Hey everybody, it's time to start our very last unit. We're going to talk about equilibrium, and we're going to divide our attack here into 4 kind of equal segments as we talk about equilibrium. So really just in this first chapter, we're just going to go through the basics about what equilibrium is and how to do a couple of the basic calculations. This is pretty connected to what we've done before, and there are some basic definitions that you're going to need to know. In general, and we've talked about this before, equilibrium is essentially in a chemical reaction when you have 2 opposing chemical reactions that are happening simultaneously and they're happening at the exact same rate. So that's when your products become your reactants and then your reactants become your products and vice versa. We're going to be looking at this thing called dynamic equilibrium, which is simply when a reaction is stressed, that equilibrium kind of shifts to reduce that stress. We're going to do a lab where we are going to stress chemical reactions, whether that be through a change in concentration or a change in temperature. And we're just going to see how that equilibrium responds. And there are some very visual and kind of some smelly and very clear-cut clues that equilibrium has actually shifted. More on that later. So as far as kinetics are concerned, we know already from our multi-step mechanisms that equilibrium can be described kinetically. We are going to be talking about the speed of chemical reactions. It's just that now it's dealing with the same equation, and the speed we're talking about is happening in opposite directions. So the same factors that are going to affect your rate laws in kinetics are also going to apply and affect our equilibriums. Thermodynamics also plays a huge role here, and we're going to see a couple connections to thermodynamic calculations later on in the chapter. So it really kind of matters kind of like how much energy is going into the chemical reaction and how much is coming out. If you shift your equilibrium one way or the other, it can become endothermic or exothermic, and that all can be related to activation energy. And if you're really not super duper careful, and we're talking about rates, if we speed up our reaction too much in one direction or the other, it can actually become super duper dangerous, or it could take an eternity to try and complete. So we want to try and keep these things in our mind when we go to set up a chemical reaction. Okay, so let's take a look at the basics of kinetics. We're just going to take a look at a generic equation. A plus B makes C plus D, and I threw some lowercase coefficients out in front so you could see how those things are going to affect our overall calculation. So we're going to start off with our basic equation here. Well, we kind of did this before also with the multi-step mechanisms, where the rate of the forward reaction is equal to the rate of the reverse reaction. So we're going to write those 2 rate laws. K times A to the A, B to the B equals K times C to the C, D to the D. The definition of equilibrium is really when the rate of the forward reaction does equal the rate of the reverse reaction. I don't think that this is anything new for us. So just take a moment to kind of breathe this in, and we'll go on to the next screen. So we're going to take that original equality statement and we're going to manipulate it a little bit. We're going to pull all of the K values to one side, and we're going to do this in a very particular way, where we're going to have K forward over K reverse. On the opposite side of the expression, then, we're left with all of the concentration and coefficient data. And you'll notice it's the products, C and D, divided by the reactants, A and B. These 2 halves of this expression are actually a constant in and of themselves. We're going to call this constant Kc, or the equilibrium constant, with respect to concentration. So there's 2 different ways that we can calculate it. Either, if we have the K values, both forward and reverse, we can take K forward divided by K reverse, and that's going to equal our equilibrium constant Kc, or we can calculate it the more traditional route by using concentration and coefficient data and taking those products divided by those reactants. We call this weird Kc thing, some books, some professors are going to call it the mass action expression, and we'll talk about that again a little bit later on. But essentially that's kind of, what you see is what you get. That is Kc. This is how we're going to calculate it. So I wanted to show you a couple example problems so that way you can finish up your homework for this particular section. Our first in-class example is actually right inside of your in-class example packet, so you can follow along. And we're talking about an equilibrium mixture. So all of the concentrations essentially are going to remain kind of stagnant if we're at equilibrium. And we're going to say we have about 0.172 moles of phosphorus trichloride, 0.086 moles of chlorine, and 0.028 moles of phosphorus pentachloride at equilibrium. And we're asked to go ahead and calculate Kc. One of the very first things that you're going to want to do is to define Kc with the actual part of the calculation. Like, how are we going to define this with concentration data? So let's do that now. In this particular problem, Kc is going to equal, again, the concentration of the products divided by the concentrations of the reactants. In this case, it would be the concentration of PCl3 times the concentration of Cl2 divided by the concentration of PCl5. And now we're left with a plug and chug problem. So I plug in the appropriate values, and then here would be my final answer. 0.53 would be the equilibrium constant. Equilibrium constants traditionally are unitless, so we get a little bit of a bonus in this section, so we don't have to include a unit. You do have to pay attention to significant figures, however, so unfortunately that's still in play. Let's move on to example number 2. Example number 2, we're going to look at the same chemical equation, but now the scenario is changing. So instead, we're actually going to introduce 1 mole of PCl5 into a 1 liter container. The system then reacts. It's going to start making some of the products, PCl3 and Cl2, and reaches finally equilibrium. And at equilibrium, we find that we have 0.60 moles of PCl3 in the container, and we're asked to calculate the equilibrium constant. We're going to have to go a little bit extra with this problem because we're going to need to know all of the equilibrium concentrations, and we have only a little bit of data to calculate it. I'm going to introduce you to something that I'm going to call the world according to Donovan. Some people actually call this the ICE method of equilibrium, and this is what it looks like. I create a chart. And in the chart, I put a separate column for each of the products and each of the reactants. I keep all of my pluses and my arrows as part of it because it makes it a little bit easier to divide. And you can see I have some darker lines in some particular places. So I like to separate my reactants and my products. And then I like to strike a line right underneath that delta. So there's 3 rows of data underneath your chemical reaction, 1 for initial concentrations, 1 for your change in concentrations, and then finally 1 for your final concentrations. So now let's start to layer some of this data inside of this world according to Donovan method. We know that initially we had 1 mole of PCl5 and 1 liter of volume. So if I throw that into my molarity calculation, that's a 1 molar solution. I also know that at equilibrium, I should have had a 0.60 molar solution of PCl3. Well, the only way that I could have gone from 0 to 0.60 molar would be if I would have added in 0.60 molar solution. Now that sets my change, and you can actually use some basic stoichiometry then to apply that change to my other 2 ingredients in this chemical equation. So we know that if there's a 1-to-1 molar ratio between PCl3 and Cl2, then the change in Cl2 must be exactly the same as our change from PCl3. The same thing would be true then of the PCl5, but notice here my signage is changing. If I'm going to be gaining product, I have to be losing reactant, so my sign changes to a minus sign. Now all we have to do is some simple addition and subtraction to figure out what our final concentrations are in each category. So now we know that we're left with 0.40 molar PCl5 and 0.60 molar Cl2 at the end. This is actually a very basic and kind of different way of envisioning stoichiometry, and we'll talk a little bit more about that in class. At this point, now that you have your equilibrium concentrations, you can push it forward and plug and chug it into a Kc calculation. So first we will start with our equation, our chemical equation, and define Kc again. Again, that's concentration of products divided by concentration of reactants. So PCl3 times Cl2 divided by PCl5, and I simply plug and chug the values now that I've calculated at equilibrium from my chart, which would look a little bit like that. And then finally, plug and chug that into my calculator and get the final answer of 0.90. One more example calculation. Let's look at example number 3. So we have a different chemical equation, and we're now given amounts of all 3 chemicals, 0.8 moles of N2, 0.9 moles of H2, and now we're going to be told that at equilibrium we have 0.2 moles of NH3 present in the container. Anytime that you're calculating a Kc, you need to know the equilibrium concentration of everything, and that tells you it's time for World According to Donovan. So let's set ourselves up for another chart. Here's my chart for this problem. Again, fill in what you know from the start. We know that we had a 0.8 molar N2 and a 0.9 molar H2. Now notice this problem is different because our coefficients are a little bit different. So let's take a look and see how that's going to affect everything. We know that at equilibrium we had a 0.20 molar solution of NH3. Now the only way that I could have gotten that is if I had added in, or my change was defined as, a 0.20 molar shift. So now let's use some stoichiometry and apply that to figure out the remainder of my ratios. So although we would want to put a 0.20 molar concentration straight across, we actually have to make this proportional now. So you can use basic stoichiometry, take that original value of 0.20 molar and use your multimole ratios. So to try and get that 0.3 for my H2, I actually needed to use that multimole ratio of 3 divided by 2. Same thing with the N2. Hopefully that's pretty clear, and we can talk about that more in class if it's not. But again, use multimole ratios to actually figure out those proportions. And notice that for my 2 reactants, because my change was defined as far as my product is concerned, they're both now subtracted values. So we go a little bit further, and we use that basic addition subtraction to figure out what our equilibrium concentrations are. And now we're ready to plug that into a Kc calculation. So let's first define Kc from our lovely chemical equation. Here's our Kc value. So it would be defined as the concentration of NH3 squared divided by the concentration of N2 times the concentration of H2 cubed. So just like kinetics, the coefficients become exponents. I cannot stress this enough. This is the #1 area of student error. You still need to pay attention to those coefficients and actually add those into the mathematical formulas. So it not only affects you in that World According to Donovan chart problem, it also affects you in the back end on the Kc calculation. This is a big deal. Let's plug and chug our numbers in. This is the easy part. We throw that into the calculator and get our final answer, 0.26. Again, a unitless number. So more on equilibrium constants in the next video.